All right, let's get right into it. We're about to pull back the curtain on the simple but really powerful language chemists use to map out the invisible world of molecules. These are called Lewis structures, and you can think of them as the actual architectural blueprints for pretty much all of chemistry. I mean, think about it. Everything around us, the air we breathe, the water we drink, it's all just atoms bonding together. But how in the world do we draw something we can't even see? How do we visualize the way atoms share those tiny little electrons that hold them together? That's the big question we're going to answer. Well, the trick is to focus on what really matters. See, not all of an atom's electrons are involved in the action. It's only the ones on the very outside, in the outermost shell. We call these the valence electrons. They're the key players, the ones doing all the heavy lifting in chemical bonding, and they're the only ones we need to keep track of. So before we can draw a whole molecule, we have to start with a single atom. You got to start with a single brick before you build the house. And we do that using a really simple notation called a Lewis symbol. It's super, super simple. Step 1, you just write down the chemical symbol for the element. So if we're talking about chlorine, we just write Cl. Easy enough, right? And here is where those valence electrons come into play. We represent each one with a simple dot. Now, chlorine is over in group 17 on the periodic table, which tells us it has 7 valence electrons. So we just place 7 dots around the symbol, and that's it. Seriously, that is the Lewis symbol for a chlorine atom. And what's really cool is that these symbols are perfect for showing how ions form. When an atom like sodium loses an electron, we just take away its dot, and now it's a positive ion, a cation. On the other hand, when our friend chlorine gains an electron to become an anion, we add a dot and put it in brackets to show it's got a negative charge. It's a fantastic visual for tracking where the electrons are going. So you might be asking, why are these atoms gaining and losing electrons in the first place? What's the motivation here? Well, it turns out they're all trying to follow one fundamental guideline. You can think of it as the ultimate rule of the game for chemical bonding, the octet rule. And it all boils down to this one number, 8. This is the magic number in chemistry. It represents stability. It's what almost every atom is desperately trying to achieve in its outer shell. So officially, the octet rule is just the idea that atoms will bond in a way that gives them 8 valence electrons. Why 8? Because that gives them the same electron setup as the noble gases, neon, argon, the cool kids of the periodic table, who are super stable and unreactive. Atoms want to be like them, happy and stable. Now, the most common way for atoms to hit that magic number 8 is by sharing electrons. This forms what we call a covalent bond. When 2 atoms share 1 pair of electrons between them, that's a single bond. And to make things easy, we usually just draw it as a single line connecting the 2 atoms. But, sometimes sharing just 1 pair of electrons isn't gonna cut it. It won't get everyone to that magic number of 8. So what do? They share more. When they share 2 pairs of electrons, we call that a double bond. And yep, you guessed it, for the maximum amount of sharing, atoms can even share 3 pairs of electrons. That gives us a triple bond, which is one of the strongest and shortest chemical bonds out there. Okay, we've got the symbols, we've got the rules of the game. Now let's put it all together. It's time to roll up our sleeves and walk through exactly how to build a complete Lewis structure for a real molecule. There's a pretty straightforward 5-step recipe you can follow every time. First, you count up all the valence electrons everyone brings to the party. Second, you draw a basic skeleton. Third, you hand out electrons to the outer atoms first. Fourth, if there are any left over, they go on the central atom. And last, you might have to do some rearranging, creating double or triple bonds to make sure everyone is happy with their octet. Let's try it with a molecule called silane. That's SiH4. Step 1, count the electrons. Okay, silicon is in group 14, so it's got 4 valence electrons. We have 4 hydrogens, and each one has just 1. So 4 plus 4 times 1, that gives us a grand total of 8 valence electrons to work with. All right, on to step 2, drawing the skeleton. Silicon is the least electronegative, so we'll put it in the center. Then we connect each of the 4 hydrogens to it with a single bond. Now hold on, remember, each of those lines, each bond, uses 2 electrons. We made 4 bonds, so 4 times 2 is 8. We've just used all 8 of our electrons. And that makes this a really simple case. Let's do our final check. Each hydrogen is happy with its 2 electrons. That's a full shell for hydrogen. And the central silicon atom has 4 bonds attached to it, so it feels like it has 8 electrons. The octet rule is satisfied for everyone. Boom. Done. Okay, so just when you think you've got it all figured out, chemistry loves to throw a curveball. The octet rule is an amazing guideline, but it's not a strict, unbreakable law. And there are a few important categories of molecules that, well, just don't play by the rules. So there are basically three types of rule breakers you'll run into. First, you get these odd electron molecules, often called free radicals. With a total odd number of electrons, it's literally impossible for everyone to have 8. Then you have electron-deficient molecules, where the central atom is stable with less than 8 electrons. And finally, you get hypervalent molecules, where the central atom actually holds more than 8 electrons, which is something you'll see with elements from the third period of the periodic table and below. And you might be thinking, okay, dots and lines, this is just for class, right? No way. Understanding these bonding rules leads to absolutely incredible Nobel Prize-winning discoveries. The scientists who figured out the structure of this amazing soccer ball-shaped carbon molecule, C60, did it using these exact principles. And now, that discovery could lead to amazing new tech, from better energy storage to brand new ways of delivering medicine right where it's needed in the body. So the next time you hear about scientists finding toxic stuff in the clouds on Titan or discovering brand new molecules floating in deep space, just remember, it all starts right here. It starts with this simple blueprint, a Lewis structure, that lets us see, predict, and understand the very molecules that build our entire universe. It just makes you wonder, what's the next blueprint going to show us?